as we were at the last few days, which has been just wonderful. I wanted to just add one story to the many great stories about Avi, which, so I met him when I was a grad student, but I was too afraid to really talk to him. And so I really got to know him when I did my sabbatical at IS about 12 years ago. And a lot of people have talked about how Avi's really wonderful with kids. So I went there with my husband and 3 young kids, and they enrolled in Little Book where Yuval was a student. And so Avi suggested that we take turns picking them up from the aftercare. So in the first week, my middle son was completely freaked out. Guess who drove me home from school? Oh, Osama bin Laden. And we tried to tell him it wasn't. He didn't believe us. And now that I saw the picture side by side juxtaposed, I figured he thought it was. I was like, okay. So, and after a while, I think we sort of needed a street cred because Osama bin Laden was driving me back and forth to school, and the son, Yuval, was in his class. So all was good. And my youngest son fell in love with Avi immediately. Didn't even know who Osama bin Laden was, fell in love with Avi. And IAS, if you spend any time there, especially when you have young kids, it's a great place to be with young kids because it's a communal environment, and they sort of run around outside and do their thing, and the parents are free to, socialize with book or prove theorems or whatever. And so you have a lot of freedom in some sense from your kids. But we took it a little too far, and we kind of lost track of miles a lot. And one time he didn't come home, and it was late, and I started to get worried. And finally, Avi brought him back, and it turned out that he wasn't playing outside with all the other young kids. He was actually going over to Avi and Ed's house, and they would be having parties or dinner things, and he would just join in. And I don't know how long this went on for, but so anyways, when I was thinking about preparing this talk, I went into my file cabinet. That's like 20 years old. I don't open it up anymore. But the younger crowd here probably doesn't know that we used to give talks with projectors. We used to have this clear paper that we would write on with special pens, and we would hand draw our slides. And sometimes you drop coffee on it, and your whole talk would be gone. Anyways, I was looking through my file cabinet because I saved some of the slides from some of my favorite talks. And I went into the Avi file, and I found a lot of really wonderful talks that he had given, that I had coveted his slides. And one in particular was from '94, a talk that he gave at Stock called The Amazing Power of Pairwise Independence. And it was just a really wonderful talk, and it was reminding me of why, what's so wonderful about Avi. It was, I don't have all the slides on here, but basically it was, took one idea, and it's a pretty simple idea, and just showed how you could apply it to all sorts of problems, some of which I heard about, some of which I never heard about before. And so here's some of the slides. It starts off, and then tons of applications. This is just a random selection of the slides. Static dictionary, BPP is continuing student 2, on and on, graph isomorphism, deterministic implication, and so on. So I thought that I would try to, copy from Avi, so that's why my title of my talk is Amazing Power of Composition. I want to talk about this simple idea of composition and how we can use it to basically, this is with a lot of people, but my own personal view is it's an attempt to try to understand Avi's work from the 90s, all those amazing circuit lower bounds that he had, monotone formulas, monotone span programs. So what I'm going to tell you about today is like a theme, which is function composition, and how you can use it to prove all of these wonderful lower bounds. A little legend, one more story. By the way, do you see this? Is Sasha here? Anyways, he does do proof complexity. I found this on the internet. Anyways, this is a legend mostly to remind me. You probably can't see, but this little guy on the right is skipping steps. And Avi can't seem to walk up steps one at a time. He skips them. And to me, this is sort of a little bit of an allegory of his life. And he told me one time when he visited and he stayed at our house, and it was a chaotic visit, really more than usual. And I remember he commented when he was leaving, "Oh, there's so many ways you can live your life." And anyways, I think Avi lives his life the way that we all should. And so when you see this picture on the slide, this is, like when Avi had a paper on the area, so it's pretty much on every slide. But that's the legend, the symbol of Avi as a talk. Okay. So I'm going to talk about a new kind of hardness amplification. The old school one was you take a function, you fix the computational model, you take a function that's hard, say in the worst case, or a little bit hard, and you produce a new function f prime that's hard on average with respect to the same computational model. And the kind of hardness we want to talk about today is hardness escalation, which is now you don't fix the computational model. You start with a function f that's hard in some weak computational model, and you want to build a new function f prime that's hard for a stronger computational model. How to do this? Well, function composition. Old, simple, trivial idea. And you want to take a function f, compose it with a function g, get a new function that's a little bit harder than the original one was. And this is a old idea. I probably am not even citing the earliest work, but these are two seminal papers that use the idea of function composition to prove the first paper to prove lower bounds, and the second paper to suggest a way to prove formula lower bounds. And so today I'm going to talk about this mostly in the context of communication complexity, and then we'll see how to apply the ideas to get some monotone circuit lower bounds. A few questions to start. Okay, so just some notation. We're starting with a function f. And f can be a Boolean function, a partial function, a search problem. I'll tell you, I'll try to tell you what it is, but it's some function on n bits, and the inputs to f are z1 through zn. And we're going to compose f with this inner function g. G will be called a gadget or an inner function. F is called the outer function, just like in TCPs. And g, you should think about it as a function typically on x cross y, where x and y are each very small domains, say 2 bits or 3 bits preferably. Sometimes they'll be bigger, but the ideal is that they're very small gadget. And the composed function, just feeds the output of the g's into the z's. Capital F is the name of the composed function. So the number of bits of capital F is, the number of bits into each of the g's times n. And it's the same g. Okay, so we want to prove the so-called lifting theorem. We want to show that if we start with our function f, where we understand, say, the decision tree complexity of f, that's a weak model, it's easy to get lower bounds for decision tree height. Then from that, we want to compose f to get a new function, capital F, and we want that to be hard in some communication complexity model. Okay? And there'll be variants on the left and the right. The simplest one is decision tree complexity for little f leads to deterministic communication complexity for capital F. But there's lots of variants. Okay? So there's always a decision tree variant of the communication variant. Okay? So there are lots of these lifting theorems now. The first one that I know of is by Mackenzie. I'll talk a lot about that one. I love that paper. But it's in the last, I guess, 10 years or so, there's been a proliferation of these lifting theorems. And as Mika said, it's a bit of a mess to explain them all. So I'm not going to explain them all. I'm just going to try to give you the idea of how these things work. And there's a blizzard of applications. And Avi had a slide on his talk back in '94, blizzard of applications. Okay, so I'm going to start by telling you about the simplest one, deterministic communication lifting. And the main theorem for deterministic communication lifting is in the Mackenzie paper, although somehow we didn't really realize it for quite a while, until the last few years. So this is the lifting theorem for deterministic communication complexity. F is an n-bit Boolean function. In this case, it can be a Boolean total or a partial Boolean function or a search problem. And the inner gadget is going to be the pointer function. So G takes inputs x and y, and y is going to be, say, n squared bit string. So think of this as an n squared bit string. That's that y. And x is going to be a 2 log n bit string that's going to point to a location in here. Okay? And you feed into f a vector of these y's and a vector of these x's. Okay? So this is a rather large gadget, unfortunately. The size of y is roughly n squared, say, and the size of the x's is, say, 2 log n. But in any case, y1 through yn, this has length like n cubed, and then x1 through xn has length like 2n log n. Okay? And the theorem, amazing theorem by Ross-Mackenzie, is that you can exactly, this is pretty much equivalent to ignoring constant factors, the communication complexity of the composed function, regardless of what f is pretty much exactly the deterministic, the decision tree complexity of f times log n. Okay. So one direction is quite easy to see, which is that if you have a protocol, if you have a decision tree for f, you can always turn it into a communication complexity protocol. So the way you should think about this, I didn't say this, that one player, say Alice, gets the x, all of the x's, okay, and the other player, Bob, gets all of the y's, and of course they're trying to compute the composed function. Okay, so the obvious protocol, once you have a decision tree, is for the players to follow the decision tree. So you have to say z2 is the first variable queried. They will first compute g of x2 and y2. Okay? And for the pointer function, the best way to do that, or the obvious way to do that, is for Alice to send x2 to Bob, so that takes order log n bits, and then they just keep going. So that's how you get the upper bound. If you have a decision tree for f, you can come up with a communication protocol where the complexity is the height of the tree times its log factor. What's remarkable is the lower bound. You can actually prove that that's the only thing you can do. And this is like the ultimate when we want to get communication complexity lower bounds. The ultimate is to show that really the only thing you can do is the obvious thing. I won't tell you about the proof. The proof is not easy, but it's a quite beautiful proof. And it really does construct from an arbitrary communication complexity protocol for the lifted problem. It actually gives you a construction of a decision tree for the unlifted problem, with even with the log n. You don't even care about the log n, but you get it exactly. So it's really nice. Any questions?
Has it been applied in the other direction? If I want to show that the function is hard for communication complexity, I can represent it as such a decomposition and go to the tree, or just for existence of our functions?
I'm not sure that's, I don't know. Okay, so I want to show you some of the amazing applications of this theorem. There's a lot of them. Just to point out that the original application was the monotone circuit depth that was in the point of the Ross-Mackenzie paper to separate the levels of the NC hierarchy, the monotone NC hierarchy. It was realized subsequently that you can, in the last few years, we realized that really what they proved was this general lifting theorem for deterministic communication complexity, and so then you can get also lower bounds of proof complexity, and you get all sorts of results in communication. Okay, so let's start with the applications to circuit complexity and circuit depth and proof complexity. So this is the high-level picture of how things are going to go. We're going to always start with an unsatisfiable formula, okay? And from the unsatisfiable formula, we'll define a rather trivial search problem associated with the formula. We'll lift that search problem. We want to start with an unsatisfiable formula such that the search problem has high decision tree complexity, because we're trying to get a good lower bound. So we do that, and we lift the search problem. We use the lifting theorem to show that from the high decision tree complexity of the canonical search problem, that you have high communication complexity for the lifted search problem. Okay? And then from that, from the high communication complexity of the lifted search problem, we'll pretty easily get these two applications. So let's just see an example of Titan. This is first I have to tell you what a canonical search problem is. So you start with an unsatisfiable KCNF formula, or KCSP. You have a bunch of constraints over the variable z1 to zn. And the search problem is just given an assignment alpha to the variables that underlie the CNF, output a clause that's violated, output a clause that's falsified by the assignment. Okay? And the lifted search problem is Alice gets her X string. Again, think about this, the X like I told you before, they're pointers. and Bob gets this big Y string, and they want to output a clause CI such that when you plug in the G, XI1, YI1, when you plug in the appropriate values here for this is the first variable to the clause, the second variable, the third variable to the clause, where you've replaced the variable by the gadget, the output of the gadget, that this constraint is violated. Make sense? So we're making the search problem harder, right? Because we're making it so that intuitively the players have to communicate something in order to get the value. For every variable that they need to know, they have to communicate something to know that variable. Okay? So that's the search problem. And we're going to apply this to unsatisfiable formulas where we can prove that we can easily prove that the decision tree complexity is high. Okay? So Citon is one of the most well-studied unsatisfiable formulas in the proof complexity literature. And it's just you start with a graph G. It's an n-node bounded degree graph. Think of it as a expanding, highly expanding graph, and think of the degree as 3 if you'd like. And n, the number of vertices, is odd. The variables are just the edges of the graph. Okay, and the constraints, you have one constraint for every node, and the constraint says that the mod to sum of the edges coming into the node is odd. Okay, so all this really is a system of more or less a random system. Since we can pick the graph at random, it's a particular system of mod 2 equations subject to the fact that every variable occurs in exactly 2 equations. Okay, and because every variable occurs in exactly 2 equations, and because the number of vertices is odd, this is unsatisfiable. Okay, and because the graph's expanding, it's actually pretty easy to show that the decision tree complexity is n. Okay, so you just have to just think of yourself as an adversary, and because of expansion, you can always go a long time before you are forced to falsify a node. Okay, before you're forced to set all the edges coming into a node to make the to falsify that value. Okay, so that's quite easy to prove. And then from the lifting theorem, we get that the lifted search problem is also hard now for deterministic communication complexity. Do you have questions? Too slow, too fast?
How good of a standard do you think?
So if it's so we tend to, it doesn't have to be that good. Yeah, there's no reason to get into details. No, nothing fancy. Yeah. It just has to be that if, for every subset of size, say less than n over 3, there's a constant number, constant times n. No, this is super easy to prove. You can do this in 10. I'm sure anybody could sit, not just Avi, could probably sit down and do this. Okay, so far we've started with our unsatisfiable formula. I showed you the example of Citon, got the search problem, which is, given in this case, given an assignment to all the variables, all the edges, find a node that's false. We lift that to the communication problem, and now we know that the lifted communication search problem is hard. Okay? And now we want to show that from that we pretty much immediately get these really nice applications. We get monotone circuit depth lower bounds, and we can get lower bounds on the rank or the tree size of cutting planes proofs. Okay? I'll just give you the idea behind these two applications. So I'm going to show you first how you can go from lower bounds on the search problem to lower bounds for a monotone Boolean function, depth lower bounds, circuit depth lower bounds. Okay, so the thing you have to see is why the search problem right here. This is heavy notation for the lifted search problem. Okay, we already have a lower bound on this. We want to see that a lower bound for this is related to that there's some monotone function associated with this. Where this lower bound gives us the depth lower bound for that related monotone Boolean function. Okay. And the monotone Boolean function is really natural. It's just a monotone instantiation of a K-SAT or K-CSP problem. So if you fix, so this
this unsatisfiable formula phi, it has some particular clause variable structure. So here's the nodes for the constraints and the nodes for the variables, and it has some fixed, structure. So by structure, I mean this bipartite graph that describes which variables are in which constraints. Okay, and given that structure, I can come up with all possible. I'm going to come up with a monotone formula where the variables of the formula are going to correspond to the truth table of this constraint. Okay, so I'm going to have, for example, this constraint here involves variables v1, v2. So the truth table here will, if it's k-sat, the truth table will list all possible values of v1, v2, and there'll be a variable for each one over here. Okay, does that make sense? So those are the variables of the monotone formula, and when you plug in a value for the variable, for each value of the variable, you get a particular k-sat instance over this graph structure. Okay, and it's monotone because the more when these variables go from 0 to 1, you have less constraints to satisfy, and therefore the formula is more likely to be satisfiable. Does this picture make sense? So I'm trying to describe a way to encode k-sat in a monotone way. Okay. So the variables are going to be for all possible assignments. You specify if you say 1, you mean that when under this assignment the constraint is true. So these are the variables. You have 4 variables in this case corresponding to this node. 4 variables here, 4 variables here. I guess 8 variables here and 8 here. Okay, and they tell you for every assignment whether the constraint is satisfied or not. It's just a truth table of. Yeah. Yeah. And the variable tells you whether or not, if under that assignment, whether the constraint is satisfied. Okay. So that's the formula that we're going to be talking about. A very generic formula, monotone sat, and it's not hard to show actually that that the search problem, the lifted search problem here can be viewed. If you just kind of tilt your head a little bit, it can be viewed as an instance, or it can be viewed as basically this monotone KCSP. So what this lemma is saying is that if you fix a particular unsatisfiable formula phi, where you have a lower bound for the search problem, the lifted search problem. So think of phi here as being our Cyton instance. Okay, and this picture here, this is just the graph structure of the Cyton instance. Okay, so this is our particular unsatisfiable phi here is Cyton, and the lemma is saying that if you have a lower bound on any unsatisfiable phi, a lower bound on the lifted search problem, you immediately get a lower bound for this monotone Boolean function. Okay, and I'll just say a couple words about it. Alice, remember for this problem, Alice is getting x, this big long string x, and Bob's getting y, and they're trying to output a violated clause. And what you do is you view x here as describing a max term of this Boolean function, and you view y as describing a min term. Okay? And the min term basically is you add all the constraints that are consistent with y, and the max term at a high level is just, you just kind of view x as the unset. You use phi, you use the unsatisfiable formula to turn this x into a max term. Okay? And here you're going to get a violated clause when you solve this, and that violated clause is going to be transformed exactly into a variable, which is a constraint that's violated. Okay? Does that make sense? Anyways, I thought I was being ambitious trying to explain this, but it's really not difficult, and I think it's natural. Any questions? Yes. Yeah, the depth corresponds exactly. It's really just the same problem. Like I said, if you view it this way, you're not changing. You're just kind of changing the way you view things. Did you? yes, I forgot to tell you that. So over on this side, I've already done Karshmer-Vidgerson. I should have put the little skipping step guy. So I'm already on this side. I already found a monotone function, and Karshmer-Vidgerson tells us that the depth is exactly the communication complexity. Thank you for that tip. Of given a min term and given a max term, find a variable that's 1 in the min term and 0 in the max term. Yeah. Sorry. I'm so used to Karshmer-Vidgerson that I even forget. Okay, great. So now just a few words on the proof complexity application. So we also want to give a rough idea why a lower bound on the lifted search problem should give us some kind of lower bound in proof complexity. And the high-level idea is from a really early paper. I didn't realize it until after, by Lovash, Naor, Newman, and Avi. And basically, I think the paper was on decision. I don't even know what the paper was on. Decision tree. For certain. There we go. So maybe there's other things in that paper I should look at. So they basically point out, I think, in the end of the paper, a connection to regular resolution. But the basic idea is quite simple. If you have a height r resolution refutation, where each line has low communication complexity, so you can view the proof is like a DAG, okay, and the height of the DAG is r, and each node of the DAG is labeled with some Boolean function that has low communication complexity. Okay, then you can solve the search problem with a low communication. So if you have a refutation for some unsatisfiable formula, the search problem, again, is given an assignment to the variables, output a violated clause. You can solve the lifted search problem quite easily, right? Because if the players just evaluate start at the top, they know it's false, and they work their way down the DAG or the tree until they get to an input constraint, which has to be violated. And they always go in the false direction. Okay, so it's so the basic connection to proof complexity is really quite straightforward, and with a little more effort, Hun and Nordstrom showed that you can also get lower bounds not just for the height of refutations, but for if you want to get size-space trade-offs for proof systems, you can do that as well. Questions? Yeah, so cutting planes is a proof system where the lines in the proof are linear inequalities, so they can be any linear inequality over any partition of the variables, has a low randomized communication protocol. Yeah, I'm just going to ignore the randomized issue. Let's pretend it has low deterministic communication complexity. And so that's why you get lower bounds for cutting planes.
The choice of the little function, inner function, do matter for this application?
Yeah, the choice of the inner function matters a lot in terms of how tight the bound is. So the one negative with the Ross-Mackenzie lifting theorem that what time is it? I have 15 minutes left? Okay, I better speed things up. Okay. So this lifting theorem, it's beautiful with one exception. The gadget size is large. And so that leads to lower bounds. The monotone depth lower bounds that come out of that are like n to the epsilon. They're not truly linear. And likewise, the proof complexity lower bounds are not optimal. In all of this work, sort of the golden standard is to get a constant size gadget. And if you can do that, basically all of the results will end up being optimal, up to constants. Yeah. Okay, so that's, you were ahead of me. So you get an n to the epsilon monotone depth circuit bound, and you can separate the levels of the hierarchy by picking the appropriate unsat formula. And because you have this, it's important that you have the equivalence, not just that the lower bound on decision tree complexity gives you the lower bound on communication complexity. In order to separate the levels of the hierarchy, and we'll see in a minute, to get these communication complexity applications, you really need this very tight control, both upper and lower bound, on the communication complexity of the thing you're talking about. So because the gadget's big, we get n to the epsilon. That's the best circuit depth lower bounds you get out of the Ross-Mackenzie lift. And again, you can get depth lower bounds for cutting planes also of something like n to the epsilon. Okay, so now I want to quickly mention some communication complexity applications of the lifting theorem. So there's a problem that's in, I don't know, maybe page 4 or something. I don't know if anybody remembers, of the communication complexity book by by Kushelevitz and Nissan. And they talk about this partition versus deterministic communication complexity. So here's a little picture. This is the communication matrix of some function. The rows are the x all the possible values of Alice's input x. Columns are all possible values of Bob's input y. And a protocol is a particular type of partitioning. In the entries, if it's a Boolean function, the entries are 0, 1. And a protocol is a particular type of partitioning of the matrix into monochromatic rectangles. And it's of a particular type because one player speaks, and that sort of chops off the matrix into two halves, and then they recurse, so the next player speaks and chops off the next two, and so on. So you get a less artistic partitioning of the matrix. A partition in general can be fancier, right? You can have things that, I think this one is not one that comes from that, but my artistic skills are a little limited. But a general partition can look different, right? You don't have to follow this divide and conquer approach. So the communication complexity, is the log of the. It's basically the log of the best partition coming from a deterministic protocol. And the partition number instead is the least number of monochromatic rectangles to cover the matrix. And the open problem was, and one other definition. So chi of x is the partition. Chi of f is the partition number of f. F's the two-player function, and it can be written as chi 0 plus chi 1, where chi 0 is the minimal number of rectangles that partitions the zeros. Chi 1 is the same thing for the ones. And sort of what you can prove using the lifting theorem plus a new lower bound on decision tree height for the right problem, you can show that there is a pretty big gap. So the communication complexity of f can be a fair bit bigger than the partition number. So it can be omega of log to the 1.5 of the partition number. Okay. Old result by Aho, Allman, and Yannakakis gave an upper bound that the communication complexity of f is never more than the log squared of the partition number. So we're still a little bit off from the tight answer. And for chi 1, which is the minimal number of rectangles to cover the ones, to partition the ones, we get the tight results. So the communication complexity of f can really be as bad as the square of chi 1. Okay. And the way that this proof goes is you first prove the decision tree analog of these questions, which is much easier. Still not trivial, but it's easier. And then from that, you just immediately get the communication complexity lower bound. So I'm not going to tell you about the decision tree separation because it's not that easy. It's not that hard, but. So we actually get the first from the second. Yeah. Okay, so that's one application. You also, from this second one, you get something about the log rank conjecture, this old wonderful conjecture by Lovash and Sachs, asking whether or not the communication complexity is basically equal to polylog of the rank of f. So can we pretty much up to a polynomial completely characterize deterministic communication complexity by just studying rank? And this is a really wonderful open problem. There's been good progress made on the upper bound by Lovett and others recently. And as again, a direct corollary of the second point is a lower bound, a tightened lower bound on the rank. So since the monochromatic, if you have a covering of the ones, a partition of the ones, the rank has to be at least that big. Okay. Sorry, I think I said it the wrong way. Yeah, I said it the wrong way. The covering number has to be at least as big as the rank. So from that, you get immediately that there exists some function f where the communication complexity is at least log squared of the rank. Okay. And I won't tell you about the third point. Clique, co-clique It's actually, the reason I'm not going to tell you about it is it uses a different lifting theorem. But this was a result that Mika proved a few years ago. The clique versus co-clique problem is sort of a famous problem by Yannakakis. And that's also can be solved in the same style. You first prove the decision tree separation, and then you lift it to get the communication complexity result. Okay, any questions? So I just wanted to tell you about a few other lifting theorems and some, what you can, other results besides what you can get out of Ross-Mackenzie. So there's a randomized communication lifting theorem that's actually quite different in style than the Ross-Mackenzie. It's really easy to prove, really easy. It's a reduction to set disjointness. So it's like not the hard work of Ross-Mackenzie's proof. And incredibly, because it's a reduction to set disjointness, it works also in the number on forehead model. So these are its strengths. Its weaknesses is that for search problems, you need to use a slightly more general version of a decision tree notion. And also, it doesn't work for partial functions. It only works for total. But it does work for search problems. So for total functions, the decision tree measure that you need is actually block sensitivity. So instead of decision tree complexity, you use block sensitivity in the lifting theorem. For search problems, we had to generalize the notion of block sensitivity to something that's called critical block sensitivity. And this was defined originally in this paper by Huon and Nordstrom. I don't think I want to get into it. It's a natural generalization of block sensitivity for search problems. And the lifting theorem is this theorem, that the randomized communication complexity so you start with a search problem S. It could be, again, it's a total search problem. Whoa. And now we're going to lift it with a very small gadget. So in the two-player case, G is this is the gadget G. So it's a 2-bit by 2-bit gadget, constant, which is really good. And what we show is that the randomized communication complexity of the lifted search problem is omega, or it's at least as big as the critical block sensitivity of the base function S. Okay. Wow. That's okay. It's like, keep you guys awake, keep me awake. It kind of goes with my champagne bottle that I had on the previous slide. Okay, so Zhang proved this. I don't know, Zhang's paper I think was underappreciated. It's a real simple proof, and he did it for total functions, not search problems. Huon and Nordstrom proved it for the two-party case, but their proof was very complicated. And then Mika and I proved it with a reduction to set disjointness, and yeah, it literally is a reduction, not such a hard reduction either. And it works in, like I said, in the number on forehead case. So you get the same result where you can, on the left, you can put number on forehead, and on this side, you keep block sensitivity. Of course, you lose something in the parameters, and as usual, when you get to log n players, it breaks down. So the number of players is you have to divide by 2 to the number of players. The gadget gets bigger, yes. Yeah. And that's the reason things. That and the fact that the set disjointness bound is not so. Okay, so this lifting theorem is better because it's a constant size gadget. It's also really, like I said, it's in some ways maybe you could view it as a cheat, and in other ways you can view it as really nice because the proof is really so simple. And we get, you have to start with critical block sensitivity lower bounds for the search problem, which we were able to prove. So n over log n lower bounds, and then that immediately gives you, that the randomized communication complexity of the search problem is high, nearly linear. And now, because the gadgets are of constant size, that leads to monotone circuit depth bounds of n over log n. And the best previous was square root of n, so we managed to beat Avi. That's a paper about matching. It's actually quite similar to how we do things in a lot of ways. That's a paper by Roz and Vigderson. And then we're also able to get proof complexity, rank lower bounds, and size length trade-offs for stronger proof systems where the lines in the proof are low-degree polynomials, say, because we have the number on forehead result. Yeah, yeah. So you would start with pebbling if you wanted to separate like NC1 from NC2. If you would just want the, I'm just showing you this because it's.
None of the later steps depend on what.
No, not at all. Okay, so then the third type of lifting I want to briefly mention is, instead of communication complexity lifting, we can do the same thing for the related notion of various types of rank lifting. Okay, and this was pioneered by the paper. What? Those people. Okay, so yeah, they really are. Okay. Okay, so Scherstoff actually was doing this a long time ago in his seminal pattern matrix method paper. He sort of got the first main result of lifting the rank, and he used that to get a variety of communication complexity lower bounds. And the basic idea of his result is, this is the same old communication matrix, but now it's of the lifted function. Okay, so it's of a lifted function. So you have the outer function f as usual, the inner function g. The two players, one gets x and one gets y. And what Scherstoff proved is that for something that's pretty similar to the pointer function, but on a constant, it can be on a constant number of bits even, that the rank of this matrix is more or less the same as the degree, the polynomial degree of the base function f, okay, the Fourier degree. Okay. But what I wanted to tell you about today briefly is two extensions of lifting rank. One to Rasbroff's rank measure. How many people have heard of it? Not many people. Good. Do I have 5 more, 10 more? How much time do I have left? 5 minutes? 2 minutes. Okay. Oh, 10 or 2? 3. Okay. Okay, so let me tell you quickly about this. Wow. Okay, so this is the same square we had before. So you have rows indexed by Alice's. This is the communication matrix. So you have rows now indexed by ones of a function. This is a monotone function, not necessarily monotone, but rows labeled by ones of the function, columns labeled by zeros of the function. And this is an arbitrary matrix A. It does not. This is not this is not like the Karshmir-Wigderson matrix that you might think. You might think that you want to fill that in with a variable that's 1 and 1. It's not that. It's just an arbitrary real matrix. And the rank measure, mu sub a of f, so you start with the function f, the Rasbroff rank of f is you want to find, with respect to a matrix A, is you want to compute the rank of the whole matrix A. Okay, that's on the top. And on the bottom, you want to divide by the maximal rank of all of the Karshmir-Wigderson subrectangles. Okay, and each of the colors is a Karshmir-Wigderson subrectangle. It's just this. It's for each variable of the function f, you have a rectangle, and the rectangle contains all of the pairs where that variable is 1 on the 1 instance and 0 on the 0 instance. So the colored rectangles really do correspond to the Karshmir-Wigderson rectangles. Okay, and there's n of there's n of them if there's n variables. And the rank of A, this Rasbroff rank of A, is you want for it to be big, you want to come up with an A where the rank is huge and where all these little subrectangles, the rank is dropped severely as much as possible. Okay, why do you want that? Because you can show pretty easily that lower bounds on the rank. If you can come up with an A, you get to pick the A, any A you want, and you can prove that this measure is large. That automatically gives you lower bounds for monotone span programs, all of these classes, monotone comparator circuits, monotone NC1, monotone log space. So in a paper that Robert will talk about in a couple days at the Fox conference, Robert, Robert, myself, Ben, and Steve, we proved basically a new lifting theorem for the Rasbroff rank. So we showed, that same style, that if you start with an outer function f, and if you can prove that a certain degree measure of f is large, okay, we call it algebraic gap, then you automatically get that the lifted problem, where you're lifting by the same inner function that Scherstoff uses, that the Rasbroff rank of this is going to be exactly equal to, more or less exactly equal to the algebraic gap. Okay, and then you can use that to prove lower bounds on the Rasborough-Frank, which then gives you pretty strong lower bounds on all those models. So just a quick picture. It gives you all these lower bounds, and Avi's favorite is span programs. I was going to tell you what they are, but I'm out of time, so I won't. I don't know if it's his favorite model or the favorite model that he defined, but we'll say it's his favorite model. Anyways, it's a really nice model. The nice thing about it is even though it's monotone, it's actually stronger than monotone. Well, it's incomparable, but it can compute things, monotone functions with small monotone span formers that you can't do with small monotone circuits. So even though it's a monotone model, it's doing linear algebra. It's actually a fairly powerful model. Using this gap theorem, we're able to get lower bounds for pretty much for all of these things, and they're exponential. There's also really interesting work on lifting theorems for non-negative rank, which I guess I don't have time for, and they allow you to prove really strong lower bounds on the size of extended formulations. So I'll just quickly conclude. So there's lots of but there's lots of problems that are closely connected to what I talked about, getting more lifting theorems for constant-sized gadgets. Bigger problems is, let's go back to the non-monotone case, see if we can be great to somehow, people have been thinking about this, but it'd be great to actually understand formulas, get some stronger formula-sized bounds, extended formulations so that maybe come up with a model of extended formulation where there is some ability for the polytope to depend on the instance, because they don't capture all semi-definite or all linear programs, and then hopefully 60 more years or more left. Thanks.
So, can you imagine or conjecture any lifting theorem for size? Depth is okay. You can do everything.
Yeah, I've thought some about that. I don't think it's out of the question, but. I don't know which paper. Yeah, that'd be great. That'd be great for proof complexity. We'd be out of business. Oh wait, I forgot my last slide. I guess I should give you these first.
Is it working?
So thank you, Ron, for this lovely introduction. So I did promise a serious technical talk, and as the title kind of indicates, I'm a man of my word. But I wanted to start by thanking Avi for his kind of contributions to me. And I want to be very, very specific about what I'm thanking him. So I'll take a few minutes for that. And essentially, if you Google obvious advice, then you get a few natural things. One is, for example, that don't throw a brick straight up in the air. Another one is don't iron your clothes while you're wearing them.